What does node 14B show? Does it show the same circuit,
Exactly.
but
There's no way.
instead of a single transistor, what do we have?
Darlington pair.
Darlington pair. So, there's my Darlington pair, which is connecting two transistors. The emitter of the first is connected to the base of the second. So there's our E. This is HFE1. This is HFE2. Okay? Let's say both are 175 and 175. All right? So, now, when it comes to the stiffness test, okay? Stiffness test in this circuit is, here's my voltage divider. Stiffness test test is HFE times RE, what? Greater than 10 times R2? That's the stiffness test. HFE here is HFE total. Right? And what is total HFE? Is it HFE1 plus HFE2, or is it HFE1 times HFE2? It's times HFE1 times HFE2 times RE. So 175 times 175 times, how much is RE? Let's say 10, same as before, 100. The only change I'm making between the two circuits is replacing the one transistor by two transistors. And we know that transistors are not expensive these days, okay? 5 cents, 10 cents, 50 cents, okay? By just adding two transistors, you make your circuit more solid, easy to design, easy to operate, okay? Times 100. So what is 175 times 175 times 100? 30? 30.6K? Are you sure? Yeah, you have to multiply times R. So you like what you get?
185,
Is that what the circuit says?
Yeah.
Sure. Doesn't matter. 175, 185, 175, 185. So how much?
3.2 meg.
3.2 meg.
Would be 15 cents out every time, so 15 times 4.
That's on the left side, 10 times R2. On the right side, which is 10 times R2 is 22K. So that's 220K. Is 3.2 meg greater than 220K? Yes. What did I do? I just changed my circuit just a little bit. Converted it from a single transistor to a Darlington pair, two transistors. And by multiplying the two HFEs, now my transistor or the circuit will appear like a much bigger load, and as a result, this circuit is stiff. Do you see that? Why it's stiff? Okay, so that's what we're going to do, is we're going to analyze the circuit that is in nodes 14 on page 4 by making a change to it, and instead of doing this circuit, I'm going to do the stiff circuit, which is nodes 14B. So do you see now the difference between nodes 14 and 14B? It's the same circuit except it's Darlington pair. Okay, so let's do a DC analysis and then let's do an AC analysis. So the DC analysis is for Darlington pair. Why? Because I want to work with a stiff circuit. It's so much easier to do the calculations with a stiff circuit. So go to the appendix on the back page of 14B. Okay? Compare it with page 2 of notes 14. So keep notes 14, page 2, beside appendix 5 from 14B like this. All right? So, VB is the voltage here. This is VB, right? Is there a change between the two circuits for VB? No. What about VE? What about VE? VE is this voltage here. Is there a change between the two circuits?
Yeah.
What is the change?
R prime?
No. We subtract 2 of these 0.7s.
Oh, yes.
0.7 here and a 0.7 here. So VE is VB minus 1.4. You see?
Pravin, if Vin is an AC source, would you double R prime E?
No,
Okay.
no. We'll come back to that. Right now we're going to do DC analysis for the Darlington circuit, okay? So let's calculate VB. VB is, let's do the, should we do cutoff first? Let's do cutoff first. What is cutoff? Cutoff is when the transistor acts open. So is that VCC? So is that 12 volts? Right? So that's the first thing. I'm going to be working with 14B, okay guys? 14B. Okay, saturation. Saturation, close switch. So, what do you think the saturation equation is? If this transistor acts like a closed switch, I've got 12 volts, closed switch, RE. So is it VCC over R IC sat? Is it VCC over RE? There is no RC, is there? So it's just RE. So is it 12 over 100? How much? What's that? 0.12? 0.12 amps? Let's write it in milliamps.